Greetings everyone. Welcome to our video series on anaerobic digestion. Today we will discuss the intricacies of performing a COD balance in an anaerobic system and understanding how to predict the theoretical methane composition of the produced biogas. Understanding the COD balance across an anaerobic reactor and knowing the methane yield and biogas composition help reduce operational and financial risks involved in anaerobic digestion projects. Since this information is crucial in designing reactors and biogas scrubbing systems. Understanding the methane potential of substrate and the theoretical composition of the produced biogas are critical parameters for assessing a substrate's potential for biogas production. In today's session, we'll explore the theoretical basis that can be employed to estimate the theoretical maximum possible methane production from a waste source and theoretical methane concentration in the produced biogas. In aerobic waste and wastewater treatment, also known as activated sludge system, the majority of the treated COD is converted into new biomass. Approximately 30 to 40% of the removed COD is transferred into carbon dioxide gas, and the rest gets utilized in synthesizing new biomass, which must be periodically removed from the process. Activated sludge treatment is a highly energy and operational cost-intensive process, necessitating sludge dewatering and disposal arrangements, along with the energy required for oxidizing the CO2. On the contrary, anaerobic reactors convert the majority of removed COD into biogas. Typically, only 5 to 10% of the digested COD is converted into new biomass, and the rest is converted into energy-rich methane gas that self-distills out of the digested liquid. This biogas can be collected and further used as a renewable energy source for various applications. Additionally, energy savings occur as no energy is required for oxidizing the waste. The low sludge yield of the anaerobic digestion process is both an advantage and a disadvantage. On one hand, the low sludge generation minimizes sludge dewatering and disposal costs. On the other hand, the slow generation of anaerobic biomass makes the process challenging to start and manage under drastic environmental and waste characteristic changes. However, if operated within the optimal operating parameters, anaerobic digestion technology is superior to aerobic waste treatment technology in terms of operational cost and net energy demand for treating high-strength solids and liquid wastes. Let us start by understanding the COD balance across an anaerobic reactor. COD does not get destroyed across an anaerobic reactor. It simply gets converted from one form to another. Since carbon dioxide does not have any COD, one can estimate methane production from the amount of COD removed by performing a COD balance across an anaerobic reactor. As illustrated through the calculations in the figure here, 1 mole of methane needs 2 mole of oxygen for its complete oxidation. If we use the universal gas law, we can find the COD of methane. It turns out that 395 milliliters of methane measured at 35 degrees Celsius is equivalent to 1 gram of COD. It is noteworthy that anaerobic reactors cannot produce more methane than the theoretical maximum amount determined by this stoichiometric relationship. In fact, the actual yield is often lower than the theoretical maximum value, since although anaerobic reactors convert the majority of the removed COD into methane, there are some losses involved in the process. We'll talk more about the COD losses in the subsequent sections of this video. Please also note that CO2 generated during the digestion process doesn't play any role in the COD balance, since CO2 is a completely oxidized form of carbon. We'll learn more about the carbon balance in the following section, as it helps in calculating the composition of the produced biogas. Carbon balance can be performed on an anaerobic reactor using the Buswell equation. The renowned Buswell equation, as shown here, provides the theoretical stoichiometric basis for the digestion of substrates in anaerobic reactors. It is noteworthy that the theoretical proportion of methane in the biogas is stoichiometrically determined by the composition of the waste, and hence it cannot be altered. This equation can be further derived to calculate methane concentration in the biogas using the COD to TOC ratio as shown here. Typically, the expected methane percentage in the biogas can be expressed as a product of 18.75 times the COD to TOC ratio. The actual measured methane production and concentration of methane in the biogas may vary from theoretically calculated value due to the factors such as a minor portion of methane and a major portion of carbon dioxide gases are being lost in dissolved form in the reactor effluent. This is because CO2 is more soluble than methane. Moreover, dilute wastes have higher gas losses compared to the concentrated wastes. Henry's law for the solubility of gases in water can be used to estimate the losses to correct the theoretical methane yield and composition. Moreover, typically 5 to 10% of the removed COD is used in synthesizing new biomass. This COD is not available for methane production. Finally, presence of oxidized chemicals such as sulfates, nitrates, nitrites that are present in the reactor substrate or additives can consume COD without directly contributing carbon atoms to the production of methane. We strongly recommend verifying the results of initial methane yield calculations using biochemical methane potential and pilot digestion tests. Details of the biochemical methane potential test will be covered in subsequent training videos. That concludes our video on COD and carbon balance across an anaerobic reactor. If you have any further technical questions regarding the contents presented in this video, please feel free to contact us at the details provided below. Thank you so much for your attention, and I look forward to seeing you in the next lecture of this video series. Bye.